think we're going to go ahead and get started. So welcome to the last Nano at Tech seminar for the spring 2018 semester. And we'll get started up again after today's seminar in August with a new schedule, and you'll see that over the summer. But just so that you don't lose all intellectual stimulation over the next couple of months, actually, in a few weeks, we have our spring Nano Fans event, which is a kind of a half-day symposium focused on the intersection of life sciences and nanotechnology. And the topic for this one on May 9th will be biophotonics. It'll be here on May 9th, starting at 11 a.m. You'll see there are flyers out by the pizza, and they just ask you to register so that you can get your free lunch. So it's a real pleasure to welcome today's speaker, Professor Dragomir Davidovic from the School of Physics. Dragomir got his bachelor's in physics at Belgrade Faculty of Sciences before getting his PhD at Johns Hopkins, and then did a postdoctoral work at Harvard and came directly to Georgia Tech after that, where he is currently an associate professor in physics. And I will turn it over to him.
Thank you. Thanks. Hello? Good. Thank you for the introduction, and I'm glad to be here. So I'm right across the street from the physics department, and in today's talk, I will talk more about what has been going on in my lab over the last couple of years and in a broader context. So our work is closely related to the field of spintronics. So I'll give you an introduction to the field, focusing mainly on industrial applications. And then I will talk about our particular research goals, which are focused around understanding the basic physics in the dynamic of magnetic switching and path to new projects in physics. And that includes the study of the magnets in extremely small limit of size. Okay. And also, we are trying to observe macroscopic quantum phenomena and novel dynamics in magnets that are highly driven out of equilibrium. And the next goal will be to move on to quantum information science to start study multipartite entanglement between single electron spins inside these nanomagnets. Okay. So, okay, something went wrong here, but all right. Okay, so what is spintronics? I call it's the electronical spin. So it is at this time it's a mature science. It's been around for 20 plus years, and therefore it is best explained by its industrial applications. And this is the most famous one. And if you buy a hard disk, for example, this is from eBay, and open it up, this is what is inside. This is a hard disk drive, and what you see here is this rotating magnet that spins very fast. And there's an actuator that can move left and right. And then there's a head. And this head here at the very tip here, it is so small you cannot see it. There is a reader and a writer that will write and read information that is stored on this disk. So let's go a little further to explain that. So how does the reader and writer work? So here is the picture of similar disk. So if this disk is spinning, there is a track, and this head floats just over the area of the track. And on this track, there are a lot of little domains where the spins can be up or down or left and right, depend on when was this made. And the read head is shown here. This is a sensor of a magnetic field based on giant magnetoresistance effect. So it turns out, if I zoom into here, you see here the domains, and here we are sending current through this sensor. And the current is very strongly dependent on magnetic field. That's why it's called the giant magnetoresistance. And therefore, by measuring the voltage drop across this sensor, we therefore see whether the domain is up or down, and that's how you read the memory. Okay, so now in context of that, our work focuses on the ultimate limit of storage density in very small particles, which I'll talk a little bit later. There are two varieties of these sensors. I forgot to mention one more thing. You can also see that there is a coil here. There's an inductor. This coil is used to to flip the domain into the desired direction. So there's both the reader here and the writer just over the domain. They come in two varieties. They are lateral systems based on GMR, giant magnetoresistance. But more recently, we are switching to tunneling junctions or tunneling magnetoresistance sensors with vertical transport. And they have much higher sensitivity than the giant magnetoresistance. So let's now talk a little bit about typical MTJ, magnetic tunnel junctions, since most of the things that we do in lab involve these junctions. So here is a typical, this is a high-level, relatively high-level magnetic tunnel junction. And it has two ferromagnets in the middle. And this is an alloy of cobalt, iron, boron, and the magnesium oxide in between. Okay. So it turns out that the tunneling resistance between these two ferromagnets depends very strongly on the orientation of these small nanomagnets. So this is now the sensor in the GMR, in the hard disk tools. Okay, so this tunneling magnetoresistance, this is the ratio of how much the current changes when the domain changes direction. So it is given proportional to the polarization of spins in these magnets. So what is the highest value of the spin polarization ever recorded? It's only 0.7. That's not very high. That's state-of-the-art, reproducible spin polarization that can be made, unfortunately. Just to give you an example, if you want to do quantum information in this system, like perform the Alice and Bob Bell experiment, P needs to be larger than 0.9. So this gives you an idea how difficult it would be to do quantum information science in the solid state. Now let's go a little bit further. So why is there, so just to explain what causes tunneling magnetoresistance. Well, it's caused by the band structure of magnets. So for example, if you have a cobalt has spin up and spin down at different energies. So the majority electrons have the Fermi surface like in copper. So there's a normal metal. But the minority electrons intersect the d bands, have a very complicated Fermi surface with a very high density of states. So if I plot the density of states of minority and majority, there will be an imbalance at the Fermi level. There's going to be a lot more electrons with, all right, so this needs to be flipped by mistake. But anyway, minority states have much higher density of states than the majority ones. And the spin polarization is related to that imbalance in the density of states. And the TMR is given in terms of this P in two sides of the junction by the Julier formula shown here. So if I have the best possible junction today made in Japan, then we'll get about 300%. Okay. So P equals to 0.7 produces a 300% ratio between the parallel and anti-parallel resistance. Okay, so now there is another breakthrough later on, maybe 10, this is now 15 years old. No more, it's almost 20 years old. This is called, another application is called magnetic random access memory. So you see, with these hard disks, there is a spinning, there's a spindle, there's actuator, there's moving parts. This is not very practical for fast applications. Instead, we need to have a fast access memory, which is known as the random access memory, which has no moving parts. And the idea of that is that if we have a tunneling junction, as shown here, with spin up and down, then if we send a large current from one lead to another lead, if it is sufficiently large, it can reorient the magnetization of another lead. So we don't need any moving heads. We just need a tunneling junction that can do both reading and writing. Okay. And here is the actual. This is much more complicated. You see that there is a little transistor here. This transistor is very important because it turns out that this type of switching, which is known as the spin transfer torque switching, requires very high current densities. In fact, they're so high that it's not practical for many electronics applications. So this transistor here is used to boost the current on a chip so that there is enough current capability to switch the magnet. Okay? So it gets very complicated. There's a lot of variants, and here is Everspin is one of the companies that makes these chips that can be bought. And you can, this random access memory has been placed in many devices, like especially on the satellites, or if you go to outer space, you have a more reliable, these magnets are much more reliable than flash or any of other types of memories. And just a very quick reminder, what is the random access memory? Well, there's an array of junctions containing these bit lines and the word lines. And then by selecting a word line and a bit line, I can write the magnetic information to be either down or up, as shown here. So using that transistor, I can send a lot of current between a particular junction to write the state. And then later on, we can read it by measuring the tunneling magnetoresistance, whether the memory is up or down. And clearly, this will be much faster than the than the speed, but it requires a lot of power. OK, so this was the general overview. So let me now tell you a little bit of what is our work, how is our work related to this. In fact, we want to make a magnetic random access memory for the qubit readout in the quantum computer. So all this problem with the power for regular electronics get exponentially higher if you want to do a qubit readout, which is much more sensitive to temperature, heating, noise, et cetera, et cetera. So in other words, if we want to make a RAM, magnetic random access, to store information from qubits, and there are many reasons this would be very good to have, then we have to solve the problem of the damping. Because damping or dissipation is the reason why we need to send too much current to write information. So the point is that if we send spin polarized current through a magnet, it doesn't remain spin polarized for a long time, but it dissipates very fast. So the result is you need to send a lot to flip the magnetic moment. So we need to reduce the damping significantly in order to reduce the power requirements and enable qubit readouts. So we are now doing basic research about that, about the damping in very small structures. OK, and here is the experiment we are currently developing. So we want to study very fast magnetic dynamics in driven magnets with the idea to move to quantum information science and study entanglement in these systems. OK, so this is just a quick schematic of the device we are making. So we're making a tri-layer consisting of hard magnet cobalt and another hard magnet cobalt, which is shown here. They play the role of the fixed layer. And a very thin and wide permalloy soft magnet particle, as shown there. And this will apply microwaves to drive the permalloy particle out of equilibrium and send it into an uncertain state. So this means that if the system is very strongly driven, actually permalloy will not be magnetic anymore. The magnetic moment will move around too fast. OK, but at the same time, the fixed layers will stay pinned because they have much higher anisotropy, and they will not respond to the microwaves. Okay, so we'll have a system that's highly driven. And then the question that arises, fundamental question, is what kind of uncertainty will develop in this particle? Is it going to be the classical uncertainty, which means that the magnetization moves too fast to be measured, it's averaging out to 0? Or is it the true quantum uncertainty from a quantum state? And it turns out, based on everything, that actually at high drive, the states actually all have to be non-classical. There will be very strong quantum uncertainty in these magnets. That's what we want to study. OK, so let me now discuss a little bit the dynamics in magnets. So 99.99% of spintronics involves classical dynamics, shown on the left. So we have here a particle with a spin, S of t. And the magnitude of the magnetization or spin doesn't change with time, and the spin can only rotate. That's the basic idea. Okay. So the magnetic anisotropy energy, so the energy of the magnet depends on the direction of this spin. And it is given by anisotropy and the magnetic field term, which is the Zeeman term shown here. And the law of motion of the spin vector is known as the Landau-Lifshitz equation, or sometimes Landau-Lifshitz-Gilbert equation, which is basically similar to, it's a vector type equation for spin vector that has a cross product, S cross, and then there's another vector here. So it moves like a torque. So basically, this is a torque type equation. Look, if you have a, if something is spinning, that's how it moves. And you see that the magnetic field is the applied field and the internal anisotropy field shown here. We need to also add damping and noise terms to properly describe dynamics. But here it gives you roughly an idea how the spin moves in a magnet. This is an idealized case. So if this is the easy axis or the magnetic field axis, then the spin will precess around the easy axis. So in this particular case, this spin will be precessing, as I've shown by the laser, okay, around the easy axis. But eventually, these precessions die out if the system is not driven because of the damping, because the energy of the excitation is lost to the heat bath. And that's what we have. Now, what about these non-classical states? If you have a non-classical state, then this completely fails. So what happens is that we have an expectation value of the spin. And the magnitude of spin can be much smaller than the S, than the value of the spin squared. So this is now quantum mechanics. It's okay. So if you remember quantum courses, that angular momentum has Lz and L squared. So when I say L squared is L plus 1. Okay. So that's what is meant by the magnitude of spin. So the magnitude of spin can be still very large. But the average value of the spin vector has negligible amplitude compared to the magnitude of the spin S. Okay, so this is a quantum uncertainty of the spin. So in order to describe such process, we need to use a magnetic Hamiltonian. So we'll quantize the classical energy with operators shown here. And then we have to solve the Heisenberg equation of motion for the spin operator. So we have to forget about this completely. And it's very similar, but also very different. We also have to add a coupling to the bosonic heat bath. And one example, probably the only example of quantum dynamics in magnets studied till to date, is macroscopic quantum tunneling of magnetization. This has been done extensively in the late 90s. Okay. Those are extremely difficult experiments, and there's not much work done now on that. Okay, so now how do we make these magnets quantum from classical magnets? So what we need to do is we need to create states which are non-classical, and in particular the uncertainty of these states has to be comparable to S squared. Okay, by comparison, the quantum uncertainty of classical states is nearly 0. So now we have to have something very different. So we'll do this in a few steps. First, we have to do squeezing, which means that we have to create extremely high anisotropy. That is to say that we make these particles about 100 nanometers in diameter that are extremely thin. And this has been done regularly with permalloy. You can make a 3 nanometer permalloy particle with 100 nanometer diameter in a slightly ellipsoidal shape, okay, which is represented by the following anisotropy Hamiltonian as shown here. This ratio of 0.002 is similar to the aspect ratio H over D. Okay. So as you see here, the energy is very large if the spin goes out of the plane, and the spin wants to stay in the plane with a very weak anisotropy inside the plane. So even if we do this and solve the eigenstates and the eigenvalues, etc., and find the ground state, it will still be classical with extremely small uncertainty. Okay? So this is not going to do the trick, but it will get us closer. Okay. So let's follow. What do we do next? Well, the next step, we diagonalize this Hamiltonian that I showed you on the previous page to see where these non-classical states are located. Diagonalize means you have to solve the eigenvalue problem of a large matrix represented by that Hamiltonian. So we use 20,000 electron spins. And this is what we find. So the results of the simulation are that what you see on the right is the energy surface of the magnet. This is the function, energy versus direction of the spin of this particle. And theta is the angle with respect to the z-axis. Okay. So theta wants to be at pi half, which means that the spin wants to be in the plane. And then phi is the azimuth. And you see that the classical surface in energy, as a function of the direction, has a saddle point. This is very well known. But this saddle point here is very shallow below the saddle point and gets very steep when it's above. That's its distinguishing nature. OK, so now I will also find the energy levels of the spin Hamiltonian, which are shown by the blue line, as shown here. So this blue line these are the dots. There are 10,000 dots here, one for each quantum level of the magnet. Okay. And they are plotted as a function of the direction of average spin, quantum average spin. And it's very interesting what we find. That all the levels are located just above the valleys and below the ridges of this surface. Okay. So these are the quantum states. Okay. So then further on, we can now calculate these. We can calculate the spin, the expectation value of spin versus these levels. At 0, there's a saddle point energy. Just ignore the top graph. You don't need that. Just look at the bottom graph that shows the saddle point. This is not working. Oh, it's working. Oh, OK, I see it. It's a little dim. All right. So this is the point. So I plot the expectation value of Sx, Sy, and Sz. So these are the three components of the spin versus energy. And what you see here, the saddle point, the average value goes to 0. And over the saddle point, because of the steepness, the spin is very strongly suppressed compared to 100%. Okay. So this is the regime of very high quantum uncertainty of the magnet. So now we actually know what we need to do. We need to basically pump this magnet into this region of energies at and slightly above the saddle point, and then we will study spin polarized dynamics in this magnet. So that's why we have now microwaves. So how do we populate the states over how do we populate these states here and along this ridge? No, this is a ridge. Well, this is done by making a time crystal. So time crystals are a type of crystals that are in the time domain. So if you apply a periodic perturbation onto the system, as shown here, by microwave fields, then we are modulating the Hamiltonian of the system. So in this particular example, we have a classical surface that's moving left and right, as shown here. So if you have a magnetization direction initially at one minimum, it will tunnel towards the other minimum, but that by the time it arrives there, the shape of the potential changes, and this is still at the first minimum. So basically what happens is there's a full delocalization of magnetization taking place classically. And it not just delocalizes, it disintegrates completely. There's no more spin vector. That doesn't exist anymore. It goes to 0. OK, so how do we? It turns out there is a very nice theory of these time crystals. How do we solve these equations? This is now the same Heisenberg equation, except we have a microwave field. There is a Floquet theorem, which is very similar to the Bloch's theorem, which is the foundation of condensed matter physics, that the wave function as a function of time has similar characteristics as Bloch wave. So they're quasi-energies and the periodic functions of time. So this is how they look. And these epsilon mu are known as the quasi-energy levels. So they play a very important role in time crystals. So this is just a very nice picture. It turns out, so we need to now find the distribution of the particle states when it is highly driven. It turns out you can no longer use the classical Boltzmann distribution. They become different. So you actually have to use a density matrix, which is shown here. I don't want to get into the details. So the diagonal of the matrix should be the Boltzmann distribution, but it's not. And they are off-diagonal elements. But it's more intuitive to go to the right. So if we now, I plot the average spin versus time, what you see here is that this goes, if I start with a particle from the ground states and turn the microwaves on, the magnetization rapidly decays to 0 because of the process of decomposition and delocalization. And this is over a very long time scale. Indeed, you see the quantum average of the spin will reach 0, but it will have some noise around it. Okay, so this is how we plan to access these states. Okay, and how do we now get, so this is now the motivation. We haven't really reached that point yet. My students are working on this very hard. And here I'm going to talk one facet of this project. So first step is, how do we measure fast magnetic dynamics? Okay, so this is the project done by Jason Dark in my lab. So we want to learn how to measure the switching very fast. Clearly, we want to measure rapidly because we want to study the dynamics of these states. So the challenge here is that we typically deal with very high resistance samples, about 100 kilo ohms. And if you're familiar with high frequency electronics, it's extremely difficult to measure fast signals from high resistance samples, especially if they're at low temperature. Okay, so here's a device that we make in our lab. So in this case, you just have a simple magnetic tunneling junction shown here. There's no island yet between two leads. So the junction is shown there, and these are evaporation shadows. I'm not sure if this is a nanofab type seminar. I'm not sure if anyone here uses the shadow deposition technique. It's probably not. So this is something that physicists like to do. It's a very prototype, small-scale fab that you can do without clean room, but you can make samples. So let me now show you how we do that. So we use a standard lithography. We do a bilayer spin coat, followed by E-beam lithography. It is in-house, development, evaporation, deposition, and liftoff. So let me show you. How does this shadow deposition work? Well, we create bridges. We make three-dimensional structures of PMMA. For example, here is a bridge. It is supported along the z-axis. And then we deposit one material, for example, P, permalloy. And then we change the angle of deposition by rotating the stage and deposit another layer of aluminum oxide, another layer of P, which is permalloy. And here we made a tunneling junction. Okay, it's very simple. We don't have any sputtering or we don't need high vacuum. So, I mean, we have pretty high vacuum, but not ultra high vacuum. Yes?
How do you keep the top layer and bottom layer from touching and connecting?
Oh, so this is governing. There's a z direction shown. So let me just show you. Oh. Okay, so you see that bridge was here. Okay, so the bridge was supported. Okay, my students know better than me, but okay, I have to reconstruct the process. So, okay, the bridge was basically, so essentially this is one lead and this is another lead, and these shadows that, okay, it's always more complicated than sketch. But these shadows cannot touch any of these two leads. So we do careful design to make sure that, you know, when you make shadowing, that there's no touches. That's very important. It's a very important point. So in this particular case, so the bridge was shown. So there were two wires. I can tell you now. I reconstructed it. So there's one wire here, and then one wire here, and the bridge was in between in this region. Okay, so this is what you see from the top of the resist. There is a wire here and a wire here. That's all you see, and then there is a bridge, which is nothing underneath except the bridge. So then basically we deposit first one wire here and another, the same wire here. Then we change the angle, actually the other way, and then then we change the angle. No, okay, sorry, and then we change the angle and then we deposit another wire here and another wire here. Okay, so basically first we did this and that, and then we change the angle and we deposit this and that. It's very simple. It's relatively simple. Okay. Yeah, my students there's a lot of designing going on in deciding how this will work. And we use a bilayer resist. We use PMMA and MAA to be able to make these bridges. Everything is bridge made. Thank you. So let's now go to the next step. So the cooling system. So we have a liquid helium problem. So we have found a scrapped cryostat that nobody used anymore. It was waiting to be trashed. And we rebuilt it in my lab and refurbished it. So this is a 7 Kelvin cryostat for now. And we made a small magnet and the radiation shields. So this is basically a glorified cryopump that goes to 6.5 Kelvin, actually. And my students have machined a lot of these things, including the magnet. So for spintronics, the fortunate thing about spintronics is you don't need much field. The switching fields are 100 millitesla at most, so that's easy to do. We don't need to be experts on magnets. We don't need 14 Tesla. That's the thing. There's no way you can do this at 6 Kelvin. Okay, so it operates at vacuum, and it has a maybe 1 hour, maybe 3 hour sample time to switch the samples, but it can run continuously. Okay, and here are some of the tunneling resistances. So when you measure magnetoresistance or resistance of the junction versus time, then we get hysteresis loops. So when the leads are parallel, the top and the bottom leads are parallel, then we have low resistance, and when they're anti-parallel, they switch to a high resistance state. Okay. So basically the way it works, I feed the field down, and then it switches up, and then it switches down, and then I feed the field up, and then switches up into anti-parallel state, and then switches down. So then, here, this is another sample. I don't understand why the student did not go further, but okay, you can ask him later. But I have to show this sample because this is the sample where most of the stuff was done, so that's the problem. I will not show this otherwise. Okay, so here you have two permalloys. So in the first case, they're parallel, and they can be anti-parallel. Okay. So now let's go to the next slide. So we have partnered with engineers, in electrical engineering, with a group of Dr. Kressler and his students. So the next step is to study dynamics. So we use silicon germanium transistors to that end. And the idea is to integrate the junction with silicon germanium transistor shown here. So we get these transistors from the Kressler's group, and we make the junctions. And I don't know what happened here. Do you
want to switch to the PDF version?
Yeah, PDF would be better. But no, this is OK. Look, this is fine. I think it's all right. So on the right, you have something known as the Gamel's characteristics of these transistors that we use. So basically, you have a base emitter voltage, and you measure the collector current. And there's a usual exponential dependence on the base emitter voltage. You don't need to understand this graph. The point is that these transistors work down to very low temperatures. They don't freeze out. So we can use for cryogenic experiments. Okay, and here is so this is for now how things look. They're not yet optimal. But here's the magnetic junction that we made in the lab. And here is the silicon germanium transistor. And this is about 1 millimeter, as you see. And then we just connect it on chip. And so the idea is we will do the amplification right here of the signal on a 100 kilo ohm junction and then send it up through the leads and measure the dynamics. So the circuit is very simple. So we have tried a more complicated amplifier, but in the end, what really works is you just put a sample to the base and use it to bias the base of the transistor and then measure the collector current as shown here as the output of the signal. Okay, So here's the schematic of the circuit. OK, so here's how it works. So here's one example in that sample that did not have that part in the original figure. So this is an example of a transistor. This is biased at very high base emitter voltage. So then we measured both the base current and the collector current. And the collector current is now amplified by 17,000. This is a enormous number. So then you can see that while we are measuring the collector current is very noisy and small, then this is the base current. The magnified or amplified collector current is much larger, and that's what we see. Okay, so this is done slowly. So this gain of 17,000 will enable us to measure it faster because the RC time constants go down by the amplification. So here are some, so now we are trying to measure rapid switching. So here is a time trace. Time is magnetic field here, by the way. So as I change the time, I change the magnetic field. And here is a switch. It's basically, there's a lot more noise because it's very high bandwidth now. But it's unmistakable that it's right there. And if we reduce the gain, we start to lose the signal at these rapid time traces. OK, so if you take a closer look, so this is about 1 million points here. This is a lot of data. So let's now look at the high gain situation. So then if you go next, we obtain, this is how it looks in a shorter time scale. And this is finally when we zoom in. And then we get the rise times of 6 microseconds. OK, so this is relatively fast. Keep in mind, this is a 100 kilo ohm resistor in the cryogenics system. This is very fast. This time constant of this rise time of 6 microseconds is actually limited by our room temperature amplifier because we use a commercial transimpedance amplifier to measure these signals, and they have a time constant of about 8 microseconds. So basically, we are bandwidth limited now by the room temperature electronics. So my students are now trying to measure this faster from using room temperature. But another thing that we already probably see, this is what my students think, that actually that there is an excess noise right before the switching, which is shown here and there. And these are the two data traces that were taken. So the red shows more noise right prior to the switching. So we already think that even though this has not been optimized yet, we are seeing some signatures of pre-switching magnetic dynamics even at these time scales. So that's a good sign. So now we are trying to make improvements. And there were a lot more traces that showed that, unfortunately, they were not stored, but remembered. So I cannot show them, unfortunately. So we need to get hundreds of thousands of these and then do the statistical analysis to prove that and to find the correlation times, et cetera. OK, so that's one project. I hope I gave you another interesting thing about this technique is that I can find the spectral density of the noise on the collector current. And essentially, we are right around here at the corner where there's a 1/f noise below about 100 kilohertz. And the noise becomes flat. And basically, it is the shot noise limit of measurement. So we are right around here. So basically, we are in the fundamental limit of measurement already, even with such a simple setup, with indium dots and sort of commercial amplifiers at room temperature. OK. All right, so I will talk now briefly about the second project. How much time do we have left?
15 minutes.
OK. So this was the title of my talk. We're also interested in the properties of very small particles. This is Grand Nunn's project. So this is the ultimate limit of magnetism. So here is an image of nickel particles on the surface of aluminum oxide. And they are like 2 nanometers in diameter. They're single crystal. You can barely see it. These images were done in the material science department. They're not permanent magnets, by the way. At room temperature, there's no magnetism. In fact, you need to go below 10 Kelvin for them to become magnetic. So it's very small. But even though they're not magnetic, there is a surprising amount of applications of these particles. Not these particular ones, But the drug delivery, they are huge in medical science, cancer treatment, and we are more interested in magnetic storage. So basically the impact, I've done some research about the impact of nanoparticles in medical sciences is probably comparable to the impact of giant magnetoresistance in our sciences. So I think it's but we just don't do biology here in our department. Okay. All right, so let's now go further. How do we measure one of these particles? We use the same technique as before. You can use microscopy. That's way too difficult. There's only one group that really does it well in the world, and they're not doing it anymore, really. So it is very hard to do. So we will do electron transport. That's much easier to do. So basically, we use the same technique as before, and then we put particles in the tunneling junction between two aluminum leads using the shadow deposition technique. And here is the image of one of the samples. So let me give you more idea. So what is going on? So these are the leads that we make by shadow deposition. There's a small overlap. And these are the particles. So you see, if you have to reduce this by factor of 5 to get here, and then you reduce it by another factor of 10, and you get this tiny square. Okay. So this tiny square is this whole square shown here. Okay, so this is what we are trying to do. So you want to just measure one. So you do this by random chance. You cannot make this using standard lithography. So this is a 2 nanometer particle, so we are better by a factor of 20 than the cutting edge technology of fabrication, which is about 20 nanometers. Oh no, it's actually now less. But how do we do it? We make them using, we master on random chance, so the student has to make 100 samples, and then they have to measure them all, do the screening, and it's a lot of work, you know. And many of them may not work. So, okay. So here is the example when things work very well. So we measure them in the dilution refrigerator, which has several cooling stages. So we go to millikelvin, and here's a cobalt nanoparticle with nearly perfect staircase. So the IV curve at low temperatures show these steps as a function of voltage. So these steps occur because they're quantized levels. So current can only go to the particle if energy level is below the Fermi level of the lead. So as you sweep the voltage, you're crossing different quantum levels, and we observe these steps. And then we take the derivative of the curve and get, this is called the tunneling spectra, dI/dV versus bias voltage. And then we can study quantum mechanics of these particles by observing the properties of these spectra. And this is an old data for just to give you an idea. So this is an aluminum particle, and these black spots are the quantum levels. And there is a magnetic field, and we see that these levels split due to the Zeeman degeneracy. And you know, with the G factor here is 1.9. So as they should. So these are definitely quantum levels. They also have avoided crossings. You can probably see it here that they are, okay, it's not very well, but there's definitely a minimum between, and they bend and avoid crossings, also as shown here. So this can only happen if you have a quantum system. You cannot have, classical systems will have crossings always. We can also study magnetism using that. A typical example is here a cobalt particle. This was also 5 years ago. So if you measure current versus field, it will show hysteresis loop from single particle. And we see here that as we change the temperature, this is from 60 millikelvin to 4 Kelvin, the switching field drops significantly. And at 10 Kelvin, about 12 Kelvin, you cannot see any more hysteresis. So that's because the particle is so small that the switching field, the memory, disappears because of the temperature effects. Okay, so now I want to talk about how do we measure the damping in these systems. So how can electron transport provide information about the magnetic damping and other dynamics? As I said earlier, we want to reduce the damping in the system. So for that, we will use spin noise spectroscopy. In fact, noise is a very powerful method to measure the response function of a system. So how can we measure, for example, a resistor of a sample? How do I measure a resistor? There's 2 ways. The standard way is to apply voltage across an unknown sample and then measure current using the ammeter. And then the resistance will be, okay, I don't know, this got scrambled a little bit. the resistance will be V, R equals to V over I. This is the usual method. But we don't need to do this. We can actually we don't need to apply voltage. We should alternatively measure the voltage fluctuations on top of this resistor. Okay? So, and the output of the amplifier will be the time-dependent current, which is noise, which is V out over RF, which is the feedback resistor. Okay? And then using the Johnson noise formula, which is an example of a very general fluctuation dissipation theorem, one can relate the noising current to the response function, in this case resistance R. So the noise per hertz of bandwidth is given by this equation. So if you know the temperature, you can measure the resistance by measuring current noise. So this is a different way. This is actually better because you don't need any voltages. So this is how we will measure the damping in magnetic particles. Okay, this is, I should have done the PDF, but. So how do we now how do we then measure the magnetic motion? So we will do a readout process. So there is a method to convert the spin motion into a charge motion. This is known spin to charge conversion. And this has been invented mainly for quantum computing, for the silicon qubits. So the idea is, in that case, if you want to do a readout of a qubit in quantum dot, like silicon. So there is a single electron qubit, which is shown here. Okay. So this single electron qubit can be occupied with one electron only, which can be either spin down or spin up. And there is a nearby single electron transistor connected to the source and drain. Okay. So now, if the electron is on the dot, then this single electron resistor will sense the charge of that dot, and it will know that there is an electron on. But if it is not on the dot, then it doesn't sense that charge. Okay, so the single electron transistor can tell whether there is an electron on the dot or not. So that's how you can actually measure spin, because it turns out that if electron was with spin down, okay, then this electron can move into the dot and then move back out. And then one can see a transient signal, which is the readout of the spin state. And it comes in a variety of ways, this Alzheimer readout. So we have something actually similar going on. So we have a spin on the dot, on the magnetic particle, that can move because of the microwaves, or it can move because of the transport, because of non-equilibrium effects. And then there is a spin-orbit coupling, where basically the energy of the magnet depends, as I showed you earlier, on the direction of the magnetization. So then if the voltage is just near the threshold of the Coulomb blockade, or those steps that I showed before, then the current becomes a very sensitive function of the direction of the magnetization. So in the particular, for some directions, there's going to be no current, and for some directions, there will be current. So basically, the noise in the current that we measured is this way related to, okay, I'll finish, is related to the magnetic noise. And then since noise can measure damping, that's how we can study damping. Okay, so anyway, so I will now have to be a little bit faster, but the point here is what we observe, this is only a nickel particle. We observe very strong magnetic field dependence of the charge noise. Okay, and here is an example of, these are the IV curves. And I take the derivative, which is the spectra. And then what you see here is that the signal, the conductance versus voltage is quiet at low field and high field, but there's a narrow field range where there's a lot of noise, just shown here. So the fact that this noise is very concentrated in the magnetic field indicates the magnetic origin of noise, that this is not a charge noise. And we have other criteria that we use to eliminate charge noise. Charge noise is a typical noise source in these type of devices, which is a plague of quantum computing and everything in single electronics. But it is very clear, these are the noise regions. This is very strong concentration of noise here. So this is, we see it in other samples. Here's particularly strong evidence. This is a higher field. There's a narrow concentration of noise shown in current at particular voltages and particular fields. Okay, so what causes this? What causes this minimum? Okay, this was nice. So if you have a, sorry, I have to go back. So what's happening at very low magnetic field, there's nothing to hold that magnetization, and there's electrons that flow. These electrons that flow start to move the magnetic moment, and the spin fluctuates in all possible directions, as I have shown here. Okay. So it moves, magnetic moment moves too fast, and then it moves slower. If I apply a weak magnetic field, this magnetic field starts to concentrate this magnetization vector towards the axis of the magnetic field. And finally, in a very strong field, the magnetization doesn't move at all. Okay? So it's pinned to the magnetic field. And that's why if you measure the current noise, there is a peak in the noise. This is in 2 samples. This is the RMS current versus magnetic field. So what happens here, at low fields, it moves too fast. So if it moves too fast, you don't see the noise. It's averaged out to 0 by the time constant of the amplifier. And at high magnetic field, it doesn't move because it's pinned by the magnetic field. And in this transitional region here, the noise in current exhibits a peak, as found out here. Okay, so now the next step is to get the damping time using the peak value of the current. So there is an elaborate procedure which I don't have the time to get into. It involves a calibration, which can be done. So the bottom line is we don't need to use any theoretical models. There is no Hamiltonians, no parameters. We can use a very fundamental way, a phenomenological way to extract the damping time from the time constants. Okay, I don't have the time for that. Just to give you an idea, how do we do the calibration of the system? That's very important. Okay, so the calibration of the system can be done using spectra. So by measuring how much these levels shift, which I show here, we can obtain the chemical potential change of the particle as the magnetic field is changing. So in any case, just to finish up, we find the following is we actually find 13 and 5 milliseconds in 2 samples. These are extremely long damping times. So just in bulk, it's about, typically in clean samples in the bulk, it's about 1 or 0.1 nanosecond for permalloy. So this is extremely long. But it's not surprising it is so long. This is a 2 nanometer particle. The qubits, quantum dots in silicon, have relaxation times of 6 seconds, 5 to 6 seconds. So that's why they're qubits. And these particles here have about 1,000 spins. So it's about having 1,000 of these qubits. So this is not unreasonable, in fact. So basically, we are now in the limit of very low damping, and we have some ideas why it is so. So this was recently published in Rapid Communications. I don't know. Okay, so future work, we want to study the entangled states. So I will probably skip most of this now, but essentially by driving these magnets around the spin 0 state shown here, we can study entanglement. And I think this is probably, I will not get anywhere if I try to explain that. The bottom line is these states of the spin multiplet that are near the 0, when they're expressed in terms of single electron state, and there is tens of thousands of them, they're highly entangled magnetic states. These are known as the decay states in quantum optics. So this is called a multipartite entanglement. And people are usually familiar with the bipartite entanglement, which is in Bell state, which is a spin singlet. So this is an Alice and Bob type experiment. So now we don't have that. We actually have something much bigger. Okay. So the properties of these magnets in these type of states around when the magnetization is strongly suppressed is that small number of electrons are not entangled. They do not violate Bell inequalities. However, if you have a very large number of electrons, they become extremely strongly entangled as a collective. So that's what we are after. So So basically the ideal experiment is to have 2 of these particles, drive them with microphase, and then study the transfer of angular momentum in that state from one to another. That is the project we're working on. Okay, so thank you. And in conclusion, so I have given a recent overview of experiments and theory in the lab. We have performed single-shot measurements of a magnetic switch in a tunneling junction using silicon germanium near the shot noise limit. And we have found very long damping times in nickel nanoparticles by spin noise spectroscopy. And now we're working on this theoretical development of time crystals in nanomagnets for future studies of entanglement. And this was done by my students, Wenchao Jiang, Patrick Gartland, Jason Dark, and Nan, and our collaborators, Victor Ying, John Kressler at Sadr from Georgia Tech. Thank you.
We have time for a question or two. Going once, going twice.
Okay, thank you.